Now next thing, a very interesting, so the velocity of transverse wave in a straight string. So let's say I'm having one string, so you have to find, or you have to plug that string at the center, let's say. So it is just going to vibrate, so it's just going to vibrate it about its mean position, and then at the same time those vibration will send in some certain direction, so which will produces your wave. So what are the different things obviously that should be necessary to produce those your waves? So obviously that tension, that string has to some tension, then and then only it will produce those waves. So that's why this T is the tension in the string. So just fixed one end of the string over here, another end just pass it over pulley and attach some weight, so that will produce the tension in the string. And then you will find that the velocity of transverse wave in a straight string is given by the formula, that is a square root of T upon mu, where mu is the linear density. So that is a linear density means the total mass upon total length, so that is a linear mass density. So this is also a very important thing. So that is how we can say that is a total mass upon total length. So with the help of this formula you will get the value of your mu over here. So again, the velocity of longitudinal waves in the elastic medium. So how the waves is going to propagate, mainly that your sound waves through nothing but the compression and rarefaction. So the particle of the mediums, they are just going to compress, again going to rarefact. So that mainly depends on the elasticity, that mainly depends on the modulus of elasticity of medium through which your sound wave is traveling. So how fast they just get compressed and again get rarefact. So that parameter is nothing but which is related to your modulus of your elasticity. Yeah, so that is why we have defined which velocity of sound depends on the elasticity of the medium. Again, rho is the density of medium. So the medium should be elastic one through which the waves are going to be transfer over there. Yeah, so this is how, again the same. So for example, you can just understand by it. Just consider one cylinder, in that just one piston is there. When you press the piston, it just gets compression and rarefaction. That alternate compression and rarefaction, they are just going to form, and the particle are just going to do that to and fro motion. If you observe any one of the particle over there, so you will find that it will just do that to and fro motions, and how that wave has been just propagated, and the velocity for which we are giving it by square root of E upon rho. And E is the modulus of elasticity, that is a Young modulus. Again, if you remember, that is a bulk modulus. Yeah, modulus of rigidity. So that is what we can say for this formula. So again, the velocity of longitudinal wave in elastic medium, that is a solid medium. So let's say consider a bar, yeah, iron bar, steel bar. Yeah, so now for this, how we will find the velocity for it? So V is equals to square root of Y upon rho, where Y is obviously the Young modulus of elasticity, rho is the density of medium. So the ratio of that, square root of that, will give you the value of your velocity. So again, this one, again the very important. So through the fluid, the velocity of your sound through the fluid, it is given by the bulk modulus. It is given by the bulk modulus. So that bulk modulus, even if you remember that, so when you just have that a ball which is made up of, let's say you can say that your plastic, yeah, or instead of rubber you can say. So when you just insert into water, so definitely just you can say that there is a pressure that has been exerted on that ball. Yeah, and that bulk modulus, if you remember that, we just define it as a dp upon dv by v. So that is how we just define that your bulk modulus, and this is the velocity of your sound through the medium is given by, that is a b upon rho. Yeah, so now based on this we will say that the Newton's formula for the velocity of sound in air, obviously everyone knows Newton, that was a very famous scientist at his era, but definitely there was a competition between that Newton's and your Laplace at that time. So Newton had said something, yeah, but then Laplace have this, just he proved the wrong. Yeah, so just we will see now that story. So what he just suggested, that V is equals to, we have seen that the bulk modulus, so upon rho. So he concluded that the sound wave are going to travel through a medium. So this is nothing but a isothermal process. So isothermal process, so if you remember that in isothermal process, so the temperature is going to be constant. So the temperature is going to be constant. So pressure is inversely proportional to volume. So just we can say that it is a PV is equals to constant. Then you can write down P dV plus V, dP is equals to 0. Yeah, again we can say that P dV is equals to minus V dP. Then P is equals to, again that is a dP, then dV upon V. So this is nothing but what? So this is nothing but bulk modulus. So instead of this you can write it down as a P. And again, if you know the value of your P, so what we generally write it down, that is a rho GH. Yeah, so that is nothing but rho GH 1.013 into 10 to the power 5 Newton per meter square. And this rho is the density of air, so that is around 1.29 kg per meter cube. So if you just put down all those values, so it has been found that, so the velocity is coming to be 280 meter per second, but which is less than that of your experimental result. Experimentally they have found that it is around 330 to 340, so which is very less. Yeah, so definitely, so there has to be some correction we have to do over here, and that correction has been found by Laplace. So there was a, you can say that, so that Newton was not agree, but definitely finally he has to agree on what Laplace said that. So it has been found that later the velocity will be 330 meter per second. Now we will see that correction. Now, so that was nothing but your Laplace correction we have to see. Now Laplace says that actually, so this is not an isothermal process. When the sound travels through a medium, so obviously he assumed that the compression and rarefaction, in compression that definitely the molecules will come closer to each other, because of which there is a more friction, and you can say for example, and the temperature is going to increase, and again when they move away from each other, there is a drop in temperature. So the temperature doesn't change during, so even if there is an increase in temperature during compression, so the temperature again you can say that get back to the normal in the case of your rarefaction. So it is a very slow process, he assumed that. But then Laplace, he said that it is a very fast process and it is not isothermal. Yeah, so this is not isothermal, but this is an adiabatic process. This is your adiabatic process, and in adiabatic process we know that PV raised to gamma is equals to constant. Yeah, and again he just finally proved that. So this P adiabatic, so we have just seen that that is a delta P, again dV upon V, so which is nothing but again whose value is given by, so this is B, and this is, you will get it as a gamma into P after taking the derivation. So this velocity now becomes your gamma P upon rho. Again now gamma depends on, that is nothing but the ratio of your Cp upon Cv, so the medium through which the wave is traveling, so that depends on that value. Yeah, so based on that you will get around that 330 meter per second. So that was nothing but the Laplace correction, where he assumed that it is not a isothermal process, but it is a adiabatic process. Yeah, so in adiabatic process the PV raised to gamma is always constant. So that was the correction made by that Laplace.